Thank you for joining this December 2020 Phoenix LiDAR Systems webinar. Our presenter today is Ira Monkfold, and he is one of our top and most experienced post-processors and also in-demand trainers as well for our software applications. Ira, I understand we're going to be doing something a little bit different this month rather than compared to our previous webinars. What's the topic today?
Today we are going to be discussing how to choose a LiDAR for a particular application. So today's webinar, kind of jumping ship over to the choices you have available to you as a customer entering or maybe expanding into your LiDAR applications. Here at Phoenix LiDAR Systems, we specialize in our survey-grade mapping systems, as well as a plethora of post-processing options from the cloud to in-person trainings to all sorts of technical analysis of data that could be collected from these systems. We have been pioneers in this industry for many years now, producing the first commercial UAV LiDAR system, as well as the first in many other aspects of this industry, train following in flight planner, a very robust cloud post-processing platform for your LiDAR data. Essentially, we've been approached with many different challenges and come up with many different solutions, and look forward to doing that even more so in the future. As this industry grows and applications grow, we will as well. And so that is why we're excited to have you here today to discuss kind of future developments of sensors and what different packages, different LiDAR systems can do for your particular applications. So how do you choose a LiDAR? If you're brand new to this world, or if you've been in this industry for decades, you understand either in depth or on the surface just how in-depth and complicated this choice can be. It's not like driving up to the car lot and saying that one looks pretty, I'm going to drive it away. A Ferrari might not be the right choice for what you're trying to do. So how do you choose a LiDAR? Thankfully here at Phoenix LiDAR Systems, we have been pioneering this choice and these options for many, many years, and are here in December 2020 availing you to the options in front. So we want to build a bridge of understanding. There's two sides of this bridge we can think of: the actual characteristics of the LiDAR, the physical properties, the optics and the intrinsics of this LiDAR sensor, or maybe you're thinking about this from the applications point of view. I'm in the topographic surveying field, or maybe I'm interested in surveying power lines and utility corridors. How do I then choose a LiDAR from either one of these approaches? So today we'll be bridging the gap between these two understandings and looking for specific characteristics of a LiDAR sensor to be appropriate for specific characteristics of a LiDAR application. So to do this, as many of you have gone through, you can wade through characteristics of LiDAR sensors and particular applications till the cows come home, very easily muddying the waters in your head of what is important, what characteristics actually matter in a LiDAR sensor for my particular application. Today we'll be building this understanding so that you can confidently choose a sensor. And to do so, we're going to dive into the characteristics that really drive these industry-specific choices. We're going to be talking about three specific use cases or user applications. These are three of the main applications of LiDAR. While this industry is growing tremendously and applications as well, these three are the kind of foundational applications for LiDAR. Utility mapping, primarily power line utilities, both in the high kilovolt and low kilovolt distribution point of view. Forestry applications, forestry mapping, in terms of biomass, speciation, and many other metrics you can pull from LiDAR, as well as general topographic survey. This can be general ALTA surveys, civil engineering projects, surveying similar to that. And then after we get through those industries, we'll open up our webinar to a Q&A discussion. Try to answer any specific questions you may have had throughout this webinar, or maybe just general ideas or general questions you have before even entering. So these are the main characteristics that we are going to be going over in terms of the intrinsics of a LiDAR system. Pulse repetition rate, beam divergence are the two more nitty-gritty factors that we will be looking at, as well as a general idea of range capabilities, field of view, and then the weight, power, price dynamic that we all have to balance in these applications. And while there are many more characteristics than this, and especially once you start considering other hardwares, other pieces of the puzzle that need to be put together, these are the factors that are really critical to understand the differences in behavior from these LiDAR sensors, especially in context to the application that you're interested in. First, let's look at, dive right into it, into the deep end of the LiDAR pool, and let's look at pulse repetition rate. This is the rate in which simply the laser system is able to emit laser pulses. These emitted photon packets range from somewhere along the range of 10 hertz to up to 1.8 million hertz. So you have a huge, huge variation in these pulse repetition rates, but they very much trade off with other factors that we're going to be talking about. As we get through these characteristics, you'll understand that while we are speaking of individual characteristics, all of these balance very finely with one another and can be perfectly poised for particular applications or thought of in a more generality for more system flexibility or maybe even platform flexibility. So pulse repetition rate is simply how many pulses are being emitted from the laser over a given period of time. So a higher pulse repetition rate, obviously you get more points, very obviously. But because you are shooting more lasers out of the system over a given period of time, the power is kind of split between these pulses. So range can often be, or is, minimized with a higher pulse repetition rate. You can see in the two graphs on the center and right here, the center one is at a pulse repetition rate of 300 kilohertz, whereas we're at 200 kilohertz on the right. So similar speed, and you'll end up with obviously fewer points with a lower pulse repetition rate, but you end up with a higher range. You can see the stacked lines there that for a given speed, we're actually able to use or have a longer range to target with a lower pulse repetition rate. So range and pulse repetition rate are directly tied to each other, as well as obviously density, the more points that are coming out. And then you add yet another factor on this, platform speed, and obviously this will dictate the point density, as well as the point spacing. So a fast speed requires a fast pulse repetition rate to make sure that your laser doesn't miss a feature that you drive or fly by. Another factor that goes hand in hand with pulse repetition rate is beam divergence. Beam divergence seems like a kind of a cumbersome topic, but it's actually a fairly simple property of a laser. In theoretical laser land, laser shoots in a finite point, but in reality there is a divergence to this beam that is emitted, and that divergence is characterized in our LiDAR sensors as beam divergence, simply as the angle in which this cone of the laser is emitted. That's much easier seen here than thought of in words such as beam divergence. A LiDAR unit emits a photon very finite from its sensor, but by the time that it hits the ground here in the center image, you can see that you actually get somewhat of a footprint. And so this beam divergence angle actually really is showing you how large this LiDAR footprint is at any given range. These beam divergence metrics range from about 0.02 to 0.3 millirads, which is a pretty ununderstandable metric. But if you apply this to different range to features, you can see that a very tight beam divergence at 100 meters really only leaves a laser footprint of less than 1/5 of a centimeter. At 500 meters, it reaches 1 centimeter of a footprint. Whereas this beam divergence, upping it simply to 0.3 millirads, at 500 meters, you end up with a 15 centimeter footprint. And this may seem important or may not, but it is very much affecting how the laser essentially focuses on different objects. Focus is a nice way of thinking about beam divergence. A wide divergence or a wide beam divergence will essentially, quote unquote, detect a larger area, but the return will not be as distinct or precise due to a lower signal to noise ratio from the return. A narrower focus, a tighter beam divergence, will allow for a greater penetration of vegetation and capture of the ground. You can imagine this image in the beginning or in the middle, a very tight cone here would largely skip much of the branches, especially in the leaf-off type of application, as well as the pulse repetition rate in combination with this tight beam divergence can help penetrate vegetation and preferentially capture the ground. Similarly, with a wide beam divergence over a forested area, you're able to capture much of the vegetation, but you might minimize the ground returns through this. So it is a balance, just as the balance of pulse repetition rate and beam divergence dictate what sort of features and how clearly they are captured. The features that you're capturing also play a factor. So we're going to be layering this cake with many different characteristics that all play hand in hand, but are all very important to understand. So now that we swam out of the deep side of the LiDAR characteristics pool, let's go to the simpler, shallower side. Let's talk about range. Range is probably one of the first things outside of price that is seen when looking at LiDAR sensors. And it seems like a very simple characteristic. But there are quite a few nuances to range that are very important to know, especially in context to individual applications. Obviously, it's a very important factor in choosing LiDAR. If your feature that you're interested in collecting is further away than your LiDAR can collect, then you are up a creek. And so this is a very important factor to understand, but just as we said before, is very much in play with other characteristics like pulse repetition rate. The longer range you have towards a target, the more these different characteristics can come into play, especially pulse repetition rate. If you think of a 100-meter scan with a given pulse repetition rate compared to a 1,000-meter scan at the same rate, your point spacing is going to be much different. Your ability to capture various features will differ. The other very important thing to note is that range capability is directly tied to the target reflectivity. Reflectivity of targets generally is seen between 3 and 80-ish% reflectivity with very black tops or maybe black coated shield wires or other very low reflectivity objects in the 3% category, whereas say brushed steel or the hood of a car being on the high end of reflectivity. The low reflectivity targets have a huge effect on range, while this effect does differ depending on the LiDAR sensor itself. So a lower wavelength system, such as a Scout, has more of effect from the lower reflectivity targets than a higher wavelength system, such as a Ranger. The lower reflectivities have less of an effect. With that said, there is always an effect. Up here in the top right, you can see the change in maximum measurement range with target reflectivity. It's important to think about range in terms of your application as well. There are many applications that don't require much range. If you were thinking of primarily using a car for a mobile acquisition, your targets might not be more than 20 or 30 meters from the sensor. Comparatively, if you're trying to acquire large areas of topographic surveys or maybe many, many miles of utility corridor, this range is going to be very important in order to collect that much data. Similarly, field of view is a fairly simple but yet very important factor for many of the same reasons. LiDAR sensors have horizontal and vertical field of views, depending on the sensor array. Multi-laser systems, such as our Scout series, provide a vertical field of view in which the multiple lasers are able to be stacked so that you have a field of view along the path of travel, as well as horizontally as this laser and mirror spin. This is important because it's obviously going to be in balance with our range, pulse repetition rate, and what's called the angular step of the sensor, which is directly related to these factors as well as the speed of the platform. If your platform is flying or driving so fast that our pulse repetition rate can't necessarily keep up with this, you'll end up with gaps in the point cloud along track. As you can see in these diagrams here, these have been prioritized and all the parameters have been tweaked and so that the point cloud will have an even distribution. And these are factors that are all being tweaked with each other: range, pulse repetition rate, field of view, speed, all to maximize the collection for the particular application. The vertical field of view is very useful for filling in shadows and other angular step, perhaps missing features, but can also result in a lower signal to noise ratio, increasing the noise of a particular return or decreasing its precision. While this seems like a whole lot of variables to literally put up in the air, that's one benefit of hopping on the Phoenix LiDAR systems plane. We have developed our own flight planner. As I said before, the very first terrain following UAV flight planner, but it continues to have other features put into it. And so these, all of these characteristics of the LiDAR, as well as your collection method, can all be balanced in our flight planner, as well as other softwares, to make sure that your point spacing, your angular step, everything is lined up in a way that you are confident that you're going to collect the data that you need for an actionable outcome. Now let's move on to the fairly fixed, but yet possibly the most critical characteristics, especially when considering return on investment, sensor flexibility, and the idea of a variety of platform choices. So weight, power, and price are really, you can talk theoretically about all the other characteristics, but when it really comes down to it, these are probably some of the most important factors. Weight and power are directly correlated with each other, as well as the idea of the maximum flight time. The increased weight, the more energy is needed to power the rotors, the UAV, or whatever else is being split between the power, and less energy is left for the sensor operation. This results in lower flying time, shorter flying times, especially when you think about the larger power-hungry sensors that also are fairly heavy. The balance of the range and field of view with this idea of weight and power and flight time is important to note. A sensor may be able to collect large areas over a given period of time, but might have a very short flight time on a UAV, effectively reducing the acreage available to be scanned in a single flight. Whereas a system that is lighter, perhaps with a shorter range or smaller field of view, might be able to collect just as much or more due to its longer flying time. Important things to weigh when thinking about your application, and especially when you're thinking about the possible platforms that you can apply these systems to. Another factor to throw into the ring is if you're collecting other data at the same time. LiDAR is a very powerful tool, but is also extremely powerful when co-acquired with other sensors or hardwares. So understanding if you're going to co-acquire with imagery, in the extent of a ground control array you may present, or maybe if you're combining this with separate acquisitions, whether it be photogrammetric or perhaps an acquisition from a different platform. So very important things to note when you're thinking about the return on investment for your system and what applications you're looking for. So now that we've talked about sensor characteristics for enough time, now that you are all aboard on this, let's think about the other side of the bridge. So the other side of the bridge is the application. We spoke to the characteristics of a LiDAR sensor and what it can avail to a user, and also potential limitations. And that's all fine and good but to apply that to actual industry is another critical understanding needed before making these choices for what LiDAR sensor to choose. So let's jump into utility mapping. So utility mapping, or I'm primarily going to be focused on power line utilities, has been a foundation of the LiDAR technology for a while. The ability for LiDAR to detect small objects with a huge range of reflectivities, such as power lines, towers, and other utility structures in these corridors, while having great detail and also maintaining a huge level of safety compared to the traditional boots on the ground. LiDAR has been an exceptional advocate for the power line mapping. UAV-sized projects, such as as-built surveys, or maybe analysis of structures for repair or maintenance, these require high densities and very detailed models, and are very important to the industry. Compared to another important application of LiDAR to the industry is the idea of the long utility corridors, say long high kilovolt corridors, in which to mitigate fire hazards or vegetation encroaching into the power lines. These are often not necessarily UAV-sized projects, say a helicopter or a fixed wing, perhaps even a vehicle, a ground-based vehicle. These are great applications for LiDAR through a variety of platforms. And so LiDAR is exceptional for this industry. How you're going to use it is the important factor. The huge breadth of huge breadth of possibilities is both exciting and important to note how daunting that can be. So when thinking about the utility industry, and then thinking about all the characteristics that we presented for the LiDAR, or your potential LiDAR, how do you combine the two? How do you bridge between the two understandings? So let's think about a general LiDAR power line collection. It's important to note, are we going to be looking at very large structures, very large power lines, similar to what we see in this top right image? Or are you going to be looking at small distribution wires, similar to the bottom left image, and we need to have very, very, very detailed, accurate mapping. These two sides of the same utility mapping coin require different approaches towards pulse repetition rate and the idea of how beam divergence and power will work with this in tandem. The range to particular feature is also important to note, as the beam divergence diverges at longer ranges compared to shorter ranges. How a small crossing line in a corridor project, or maybe a tiny little phone line going to a house for a mobile acquisition, how are these features going to be collected and prioritized with your pulse repetition rate? Once again, with range, the reflectivity is very important to note. Coated shield wires have a very low reflectivity, as we said before, whereas solar panels, like in this image here, car hoods, maybe steel substation structures, all present very high reflectivity. So it's important to understand for a given power line survey, you're likely going to be encountering many different reflectivities. And just as we said before, the platform or the size of a particular scan is important to note. Are you going to be needing a platform agnostic LiDAR sensor? So one that can be utilized site specific with a UAV, or maybe utilized on a helicopter to get 20 miles of power lines in a single flight. These are important things to note in terms of potential projects that could be in front of you in terms of the return on investment that you would get from your sensor. So we've recommended a few sensors from our portfolio that you can see at phoenixlidar.com under the products tab. So we've broken this up into a few different platforms, a few different approaches towards the utility mapping industry. For UAVs, we highlighted the Scout 32. Scout 32 has exceptional density and very high precision for the Scout systems, and is very well situated for lower AGL site-specific acquisition. This system, while is not terribly heavy, will not be tremendously useful for dozens and dozens of miles of power line acquisition, but site-specific, substation-sized, as-built type of surveys, it will excel. Many applications for utility surveys are going to ground vehicles, especially when you think about distribution lines and more urban power line situations. The VUX1 HA has exceptional accuracy and precision, especially at shorter distances, making it great for the distribution side of the modeling. Whereas the Scout 16 really does excel at general mobile surveys, especially at higher speeds, as the 16 lasers allow you to minimize any laser shadowing. For helicopter or fixed wing approaches, the VUX1 LR has exceptional accuracy and precision, and is very reliable at multiple ranges, making it not only useful for a helicopter or fixed wing, but also usable on a UAV platform. The VUX 240 adds an extreme level of point density and even more range capability, but its weight and power draw make it not really UAV capable. And you can see the general idea of the max ranges here with our table on the right. And while these are 6 sensors that we have highlighted for this, this does not mean that for your given application or even combination of applications, that these are the only. You may be wanting to utilize this LiDAR choice for both utility and topographic modeling. And so to balance both of those, obviously there are more characteristics and approaches to balance. With that, let's move on to our next industry. Let's look at the forestry industry. So some of the first use of aerial LiDAR has been in the forestry industry. The idea of tree counts and general idea of biomass has been accomplished with LiDAR for years. And the forestry industry has gained tremendous efficiency through the implementation of LiDAR. Large stands can be surveyed safely and quickly using LiDAR, both in a targeted survey for particular plots or stands, or in a wide area approach for larger biomass and forestry inventory purposes. LiDAR has been developing the forestry industry even further through tree segmentation, through use of other optics, say hyperspectral or multispectral cameras, in combination with LiDAR, provide incredible optic understanding added onto the depth of the geospatial geometry understanding represented through LiDAR. While it's been primarily an aerial-based industry when thought of LiDAR, terrestrial approaches also have been gaining traction recently, especially in efforts towards diameter breast height measurements, measurements directly from the cloud for diameter breast height, or other understory metrics that are less easily captured from an aerial perspective. Additionally, leaf-on or leaf-off perspectives or characteristics of the forest present different characteristics that you can pull from the data. Leaf-off scenarios allow a easier capture of the ground and probably a better understanding of the height of the tree, whereas a leaf-on provides a better understanding of biomass, the stratification of understory and overstory, as well as avails itself to more of the optic perspective added onto the geometry of LiDAR. In order to choose a LiDAR sensor that seems appropriate for forestry industry, it's important to think about, once again, the scale of your project and also the nature of the features that you're scanning. Leaf on or leaf off, once again, is a very important factor to note for forestry applications. Are you surveying forestry to provide a good ground model in order to maybe do construction in the area? If that's the case, then leaf off will be likely your ideal target area and target season. Leaf on provides, once again, much more understanding of the habitat, a very good understanding of how fire prone a given stand is, as well as general vegetative health. So whether you're trying to capture the geometry of the forest itself, the ground underneath it, or a combination of both, really dictates once again, the pulse repetition rate and beam divergence of your system. A tight beam divergence will be able to capture the ground very, very well, but without a very high pulse repetition rate tandem, you may miss detail in the midst of the trees itself, the actual vegetative structure. A larger beam divergence, a wider beam divergence, will allow you to understand more of the depth of the forest if you have enough power to dictate multiple returns for your system. A wider beam divergence may capture a few branches as well as the ground in a single pulse, returning perhaps 3, maybe even 5 different returns for a given pulse. Once again, range, as we said in the very beginning, with pulse repetition rate has a large factor to do with that. So once again, are your approaches the large scale, high altitude, large acreage perspectives, or more of a targeted approach, more of UAV small scale targeted approach? With that, we have once again isolated or highlighted a few sensors that we recommend for forestry survey. Largely chosen because of their pulse repetition rate and beam divergence. These sensors have been proven to be very useful in these environments. And once again, you have to think about your application or your potential use case in terms of these sensors to make sure that your return on investment is highlighted through these choices. So we provided 2 different UAV approaches. The Scout Ultra is the Scout series sensor that has the smallest angular resolution that really helps the vegetation penetration. So you have a very good ground return from the Scout Ultra, but also due to its 40-degree vertical field of view on top of its 360 horizontal, you're able to collect oblique shots of both the trunks and the branches, and have a pulse go through more vegetation before it hits ground, at least at the higher vertical field of views. This allows kind of a great duality of ground capture and a good perspective of the structure of the vegetation being scanned. Conversely, the Vox UAV has an extremely high precision and a very tight beam divergence, making it very effective in penetrating large forest structures or even tall trees with thick underbrush. Two sides of the same coin in terms of how to approach the UAV perspective. For the idea of using a mobile application, whether that would be a pedestrian with a backpack, a LiDAR sensor on a backpack, as you saw in previous image, or perhaps a car or other vehicle, just to add greater depth of knowledge to the understory and the ground and trunks of the particular forest. The Scout 16 provides a very versatile collection method for a variety of platforms, mobile, pedestrian, and UAV, and can be a very helpful tool in advancing applications or providing advanced metrics to the forestry industry. And for a helicopter or perhaps fixed wing approach, we're going to highlight again the Vox LR and the Vox 240. The Vox LR has the advantage of being UAV, being able to be deployed on the UAV, whereas the 240 draws more power and is heavier, requiring a helicopter or fixed wing, but can acquire a tremendous amount of data in a small amount of time from a very large range. So our last industry of interest that we're going to highlight is the topographic survey world. This was probably the start of LiDAR industry, especially in aerial perspective, is essentially creating a very detailed understanding of a landscape, largely the ground in a given landscape, but also ideas of the digital surface models, so canopy model or And as the technology continues, adding RGB information to it, as you can see in our layer cake on the right. LiDAR has benefited the topographic surveying world tremendously, largely in efficiency and safety, keeping boots off the ground, keeping the hard hats away from trees falling down, just having a couple operators out in the field to survey many, maybe perhaps hundreds of acres, perhaps even thousands of acres, compared to the whole crew going out surveying. It helps both safety and efficiency. And once again, this feeds right back into the return on investment for purchasing a LiDAR sensor for these applications. How much work you can get done with a LiDAR sensor compared to a crew of 10 surveyors can be quite significant. While they don't necessarily replace each other, they can be used in tandem with great effectiveness. And obviously, LiDAR's penetration through the forest canopy has made it very applicable for this use. Remote areas are easily surveyed without, once again, getting people in the forest in danger. And from that, these actionable data products can be quickly created. So when we're thinking about a sensor for topographic surveys, reliability of accurate detections, primarily the ground, is really what we're going to be focusing on. Obviously, project area and flight time need to be balanced with this. Shorter, lower AGLs, lower heights of flight produce greater density, but you're not able to collect as much area in a given period of time. All of these things need to be balanced in order to find the sensor that will likely hit all the marks you're looking for topographic surveys. Small targeted topographic surveys like update to a construction or maybe detailed mining surfaces, or even perhaps an area where you're doing multiple surveys and doing a change analysis. These type of surveys are perfectly poised for the UAV market. These smaller targeted areas allow for greater flexibility of your resources, as well as greater flexibility in timeline. The more traditional large wide area mapping projects require a longer range sensor, unless you are willing to send your UAV crew out for multiple weeks at a time. The efficiency and the return on investment from a helicopter fixed wing approach, when you're talking about hundreds or thousands of acres, can be monumental. And so obviously this will require a choice at LiDAR that will be applicable to these platforms. And one other essential thing to think about is if, while we are speaking solely about LiDAR here, are you going to be co-acquiring with an imagery of any sort? And if you are, there's a very good chance that camera footprint is much smaller than your LiDAR, thus reducing your effective acreage being able to be covered by a LiDAR. So if you're deciding to choose on a Vux LR that you're going to be flying from 500 meters, there's not a great, that's not a great option if you also need to have it colored by a very small, low resolution camera. Those two hardwares don't work well together. So making sure that you have a good idea of that, or at least know how these different hardwares factor into each other, is key. So our highlighted sensors for the topographic industry focused on two different UAV platforms. First off, the Mini Vux 1 or 2, we offer both in our portfolio, has tremendous precision and wonderful reliability of capture. It's a very light system, so it has very long flight times and provides great accuracy and precision. Scout 32 has 32 lasers with a 40-degree vertical field of view. So the density of capture is much higher with the Scout 32, but you have to balance some thickness of ground surface, some lack of precision. So if you need a very, very precise ground surface, UAV, in the UAV perspective, the Minibux is likely going to perform better, but Scout 32 has a tremendous density as well as flexibility in platform, as well as flexibility in sensor parameters as well. For the mobile side of topographic surveys, these are generally roadside surveys, so detecting not only above ground features, but also very tight understanding of the ground around perhaps highways or streets or other things that may be interesting in terms of the Department of Transportation or similar field. The VUX-1HA provides exceptional accuracy and detail, and especially at the ranges that you generally see for mobile acquisitions, the VUX-1HA blows most other sensors out of the water. And once again, for the helicopter or fixed wing approach, once again, our VUX-1LR for the flexibility of platform, being able to use it on a UAV or mobile acquisition is fantastic for flexibility, but the VUX-240 really provides exceptional range and exceptional penetration and accuracy at nearly any normal range. And while these are features or sensors that we are highlighting, there are a plethora of ways of approaching these industries and these ideas, and a variety of sensors that can be utilized for these industries. With that said, there are a lot of options. You have likely seen a lot of different characteristics of LiDAR sensors, as well as many other pieces of the hardware. So let us help you choose. Let's help you choose and give you the information to allow you to make the most informed choice possible. All of these things can be fairly convoluted and factor into each other, but we are really here to help you through these choices, understand these characteristics, and provide the system that best meets your needs. So let our technical understanding guide your practical approach to an actionable outcome. With that said, I'd love to open this up to questions and answers. I have a few people on the line to help me help you. So what questions do we have?
Yeah, we got a couple questions, Ira. The first one is regarding returns. The question states, for one beam, only one depth value is provided. What happens with the other potential returns? Does the laser somehow choose one of the returns? I think your the beam divergence slide towards the beginning of the deck might be able to help illustrate how the multiple returns with a single laser work. Can you
yes,
speak?
I can go back. Yeah, I can go back to that slide and speak to that. So how the sensor chooses which return is seen is largely due to the power emitted by that particular pulse. If it has a very high pulse, high power in that pulse, every single object in that cone of beam divergence will return as a return. You can see on the right side of this cone, the power graph left to right shows that our first return was the weakest, whereas our last return was the strongest. So for, let's say, our VUX-LR that has plenty of power, it picks up all three of these returns. But let's think of a sensor that has slightly less power, or perhaps the same amount of power over a wider beam divergence. You might only catch the third and second return, whereas the power of the return emitted to the receptor is enough to dictate a return, whereas this first return might be under that threshold. So it's a matter of how much power is being emitted by the given pulse, and then the power of those returns.
Just to add to the confusion, I think it's also worthwhile to mention that different LiDAR units have different capabilities in resolving multiple returns. Like if you were scanning over the green of a golf course where points would be 2 centimeters apart, then there's sensors that can see those 2 returns and discriminate them, and maybe place points at the bottom or top of the grass, and others that would just say, well, that's a rather wide return, but it's 1 return. And it really depends on the signal processing in the LiDAR to determine that minimum distance between 2 returns of a single shot. And for example, the real units also give you a measure of how wide was that return, that reflectance. So you would know, did I hit a surface spot on at the surface normal, or was it like a flat incident shot into something soft like deep grass? So there's quite a bit of difference between the data that you get from those units. Sorry for interjecting, Ira. Thank you.
Oh, of course, thank you.
Great. Okay. Well, thank you very much. Our second question is asking about the difference between the VUX1 UAV and the VUX1 LR. That would be our Ranger UAV product and our Ranger LR product. Other than the differences in pulse repetition rate, I think the UAV has a maximum PRR of 500,000 pulses, and the LR has 750,000 pulses, if I'm not mistaken.
That is
they're both
correct.
1350 nanometer laser systems, and they're both single laser systems. What is your experience with being on the post-processing side and having worked with data from both sensors? What are your experiences with the differences between the two?
Both sensors perform very similarly. I'm actually always very pleased when those sensors end up in my computer. The VUX LR provides obviously greater range than the UAV, has a greater ability to have a higher pulse repetition rate, which aids in that additional range. But that additional range and pulse repetition rate creates, while they both have the same beam divergence, if you think of the VUX LR being targeting the same feature from twice the distance, your beam divergence is twice that. So the effects of beam divergence in terms of power of returns, as we were just speaking of, is the main difference between those two systems. With the same beam divergence, the VUX LR having a higher pulse repetition rate, maximum pulse repetition rate than the UAV, and a longer maximum range, basically exacerbates the effects of the beam divergence on a given feature.
Is the UAV a little bit more precise than the LR? Let's see, the Ranger UAV, the maximum recommended scan height is about 120 meters, if I remember correctly. Do we see a little more accuracy with that sensor over the LR because of the lower range?
I would say that given the same range, you'll see them perform nearly identically. But the ability for the LR to go to a higher range, while that is an ability to detect targets, you will get a worse precision from those larger ranges. So you can see that idea from 2 different sides of the same coin.
Okay, great.
I think they have a 5 millimeter difference in spec in terms of accuracy and precision. That's often hard to make out, right, in
Yes.
post-process data, especially if you shoot from far away.
Yeah, if you take 100 meters and extrapolate that into half a millimeter, half a centimeter, and then add in the variabilities of GPS and IMUs, it's very hard to see that difference.
Well, I guess it does show is in mobile mapping, and that's where there's a really important difference in that the minimum range of the LR is 5 meters, and the minimum range of the UAV is 3 meters. So if you have this on a car, we had people put LRs on a car, like low on the bed of a pickup truck, and then they wouldn't scan the road just below the scanner because it was just below the minimum distance. So yeah, there's always those gotchas if you want to abuse an LR for mobile mapping.
Yes, and that's why believe you wouldn't see our LR on our mobile side of things for recommended scanners. The VUX HA provides that hugely accurate and precise perspective from a mobile. And that's what I would recommend if you're looking for that from the mobile perspective.
All right, the next question we have is one that I've heard quite a few times over the past few years. How many sampling points per square meter are required for power lines? Power lines are obviously very thin and the laser beams are very narrow, so it's not easy for LiDAR to detect it that easily. What are your recommendations? Are there any techniques that you would propose?
Well, pure density doesn't necessarily dictate whether you're going to capture a power line or not on a given scan. The characteristics such as we've been talking about today, making sure your pulse repetition rate and angular step and beam divergence are all in tandem with each other for your given platform speed, so that your laser is never crossing over a thin object, either in the angular step as the sensor moves down its flight path, or in horizontal. So if your pulse repetition rate is too low, your beam might miss it as it's scanning horizontally. Those are really the most important things to note when you're thinking about small objects, finite returns like that. Obviously, if you're collecting data at 4 points per square meter, you're going to miss a tremendous amount of power line information. So with that large caveat out there, I would not recommend anything less than 30 points per square meter for general power line mapping, but would very much recommend over 50 or 75. But once again, putting your eggs in the density basket is not necessarily the correct basket to approach collecting power line data. Think a bit about how your laser actually interacts with these for a given platform speed.
Okay, let's change directions a little bit. And here's another question that we hear a little bit about often as well. How many GCPs are needed, and what would be the geolocation accuracy for different families of sensors?
I recommend a similar ground control array for whichever scanner you're using. My idea of ground control array is much more project specific, acreage specific. Thinking about a general UAV project, say 50 to 100 acres, I would love to see at least 20 ground control points. While if this 50 acres was in Saskatchewan, in snowy territory with no hard surfaces anywhere to collect ground control points, I could see why you would not collect up to 20. And while these ground control points are very important to assess geospatial accuracy, absolute accuracy, they're not actually going to increase the range accuracy of your LiDAR sensor. So they're going to enable your collected point cloud to be assessed to the geospatial accuracy and reported that way. And that is why you want to collect many ground control points, so you don't have a statistically skewed accuracy assessment. But in terms of that absolute number, that's a pretty tough one, especially given the specific project areas, because you want to target clear, hard surface areas in your project to place ground control points on. But from my post-processing point of view, putting my idealistic hat on, I'd love to see at least 20 ground control points in a given scan. Obviously, much more if you're looking at thousands of acres.
All right, we have a couple more good questions here. Are planes able to fly slow enough to gather forestry data? And what are the recommended options for large forestry areas? A large UAV, a helicopter, or planes? And if the answer is within UAV side, maybe the sales team could chime in with what UAV's offerings would be recommended for forestry.
Yeah, well, to be honest, forestry application of LiDAR really started from the fixed wing plane approach. So that's certainly a possibility. For our sensor portfolio, I'd highly recommend either the VUX LR or the VUX 240. Both, given the speed that traditional planes fly, will give you decent coverage. You may not get into the hundreds of points per square meter type of range, although with the VUX 240 that is very possible. But obviously that is dictated by flying height and speed. For the UAV side of things, depending on if you're in the United States or what your country's requirements or limitations are to UAVs, vertical takeoff and landing platforms are CW20 and 30 options are very good ones for large capture of wide areas from the UAV point of view, but I can allow sales to take that one on a little bit more.
Do you have anyone from sales who might want to chime in? Okay, we'll see if we can answer that one offline. All right, let's go on to the next question. I just want to get a couple more before we close it up. Let's see. And this is another good question. Is density affected by speed, or more specifically, could you overcome lower densities by capturing at a slower speed?
Yeah, very, very good question. Yes. So that's a great question because that's a really simple answer. Yes. You can increase your density by moving your sensor slower. There is a limitation to that. Trajectory post-processing does require a certain amount of speed. Snails are pretty hard to, well, I guess UAV snails are hard to trace because they don't leave that little trail behind them. So figuring out a good post-processing solution for a very, very, very slow trajectory can be challenging, but I bet you at that point you're going to be challenging your pilot's patience more.
Okay, and let's do one more question. It's just a bit of a follow-up on the LR versus UAV versus HA question. The question states, would you say the HA or the UAV is a better overall sensor for both mobile and UAV applications? He doesn't anticipate putting anything on a helicopter. Let me first start off by saying that the HA is a short-range sensor, and that we really usually don't recommend flying it. It's very recommended for mobile application. That's where it really shines. The UAV does have a little bit more flexibility that it is usable for mobile, and it's a very good aerial sensor as well. Do you have any more input you want to give on the LR UAV HA topic?
No, actually, I think you hit it perfectly. I think the HA is unbelievably perfect for mobile applications, but has some significant limitations for UAV applications. I wouldn't want to have its returns go much further than 60, 80, 100 meters. And at that point, also the putting that unit up in the air, the return on investment isn't necessarily there if you think about the VUX HA as a UAV-centric sensor. Similarly, the VUX LR, I wouldn't put on a mobile platform. And so the VUX UAV kind of splits the difference between the two. It's versatile enough to be thrown on a truck as well as a UAV. But you're not really going to be able to put it on a helicopter like you would the VUX LR. So that's the kind of, they overlap each other in use cases, but not completely. But Lido, I think you spoke to that perfectly.
Thank you. Okay, well, let's do one more question. For forestry application, how would you compare the Mini Ranger 2 versus the Scout Ultra? Given that the Mini Ranger 2 can have multiple returns and has a smaller beam divergence than the Ultra, whereas the Ultra has a long range and a 32 laser array.
I would say they have very different use cases for a forestry application. The Mini has very tight beam divergence, but far less density as it's a single laser compared to 32 from the Scout Ultra. Scout Ultra, I would prefer for a forestry application. Even though you might not get quite as tight of vegetation penetration for a given beam, the fact that you have 32 of them It's not really a gambling person, but that increases your odds considerably of penetrating vegetation than just one laser. And also simultaneously, if you get that one laser that hits the ground, you have 31 lasers that will give you a better understanding of the features above it. And so I prefer the the Scout Ultra in that application. If I was able to fly slowly to increase density and was really wanting to get high precision returns from ideally the ground, then that application I might lean towards the mini bucks. But generally, I would probably prefer the Scout Ultra.
All right, thank you very much, Ira. I think that will do it for this webinar. Well, we really appreciate everyone who's attended and everyone from around the world who is interested in our product. This webinar will be available on our website, phoenixlidar.com, in the next week. And we look forward to seeing you in our next webinar in January 2021. Thank you very much, everyone, and you guys have a good day.